Yes. Thank you very much. And so I wrote a lot of things on the board before you came in and sat down, but only because I don't think you need to copy it. It's really just there for visual reference. You don't need to copy it in part because you should have all received this short memo where all these formulas are explained. And it's OK to treat most of these formulas as more or less non-intuitive things. And most of the lecture might be a good mindset to think about it as your advisor gave you the task of taking this formula like this in some paper, and she would like you to implement it and get it working and play around with it or something. And so that's kind of the goal. We're going to learn by doing. But because we have actually talked about the recursion relations before, I wanted to start this with just a few minutes and just kind of give you a small idea of where some of these ingredients come from, because it's a fairly different looking representation than what we derived diagrammatically. I don't have time to explain the beauty and motivation for momentum twisters, although I would really love to. But the basic idea, for this lecture at least, we can just take an extremely pragmatic point of view, which is that before we had these, but in the last 3 lectures, we spoke about things in terms of spinor helicity variables. And the idea here is to trade the set lambda tilde and eta tilde, which labeled the fermionic parts of the amplitudes and the spinners, which are always constrained. They're a universal part of every superfunction, which are always or universally constrained by supermomentum conservation, which is delta. Remember that the lambda and lambda tildes have to be orthogonal to each other as 2 planes in n dimensions. And also there's the fermionic analog of this, which is lambda dot eta tilde. So every single, and in terms of the Grassmannian representation we had before, we had lambda dot c perp, and we had c dot lambda tilde. And remember, the c had to contain lambda. So this was always part of those delta functions inside our Grassmannian representation. So we want to trade these things that are not free. You can't just pick random 2 by n matrix lambda and another random 2 by n matrix lambda. You have to constrain them a bit. So trade these for what we're going to mu and eta, which are unconstrained, completely free, and linearly related. This is very important for the non-ugliness of this formalism. Linearly related to lambda tilde, eta tilde. So, and in particular, the map is that we have, if given a generic 2 by n matrix mu, we can associate lambda tilde by mu dot q. I'm going to define this in a second. And we can associate eta tilde with eta, a generic set of fermionic things, dot q, where q is something, an n by n matrix that annihilates lambda. If you remember that my dot is really dot transpose and you follow these definitions, if you put in, well, you can put lambda tilde dot lambda instead of the way we normally write it, and you can see that if q annihilates lambda, then clearly lambda tilde will annihilate q. So mu is really just representing some particular 2 by n slice of the orthogonal complement of lambda, which is a linear space. And note that rank of q is n minus 2. But it's an n by n matrix, and so it's not exactly unique. There are some choices to be made, and in the memo that you should have received by email, these choices are explained, or the best choices are explained. And in terms of these, mu's and etas, momentum twisters for the 8th particle are just a generic 4 vector, really thought of as an element of P3, but we write that always in homogeneous coordinates. So we'll say C4, which is really as simple as you could think. It's the lambda of the 8th particle combined with the mu of the 8th particle. And dual conformal invariance, which we haven't really talked about, acts as SL4 transformations on this. And so the dual conformal invariant objects are determinants as before. So the only SL4 invariants you can write down are 4 determinants involving 4 twistors. So just like we had for the 2 brackets, so this is the only kinematic thing we need to care about here. Okay, now one thing that's interesting about the particular linear map that is in the memo is that you can really view the super Park-Taylor amplitude as the Jacobian in the change of variables. I don't know, historically I think it was probably just said as that the momentum twister thing was the ratio function, which is the general thing divided by this Park-Taylor superfactor. But I mention this because when you do this, you get this unconstrained superfunction involving z, but you'll notice that k, which was previously in the previous lectures, was counting the size of the matrix of coefficients, of fermionic coefficients. We lose 2 of the fermionic coefficients when we remove this piece. And so that's why k in this lecture is -2, what we were talking about before. So before we had Park-Taylor, we said k equals 2, 2 incoming, the rest outgoing. Well, we're going to subtract 2 from that. And so Park-Taylor is n to the 0 MHV. And if you divide by super Park-Taylor, it's 1. So the formula that the form that the recursion relations take inside momentum twisters is relatively straightforward. It's just products of these R's. And you'll notice that because the MHV, the k equals 0 pieces, are all 1, this recursion relation is eventually just going to hit a bunch of 1s times R's. So the R inside there is where all the magic happens, that R in the middle. And the only place where something non-trivial happens is because the amplitudes which then get recursed in terms of their R's involve these shifts. And these shifts have a certain geometric meaning, which I can explain probably visually a little easier than I can explain algebraically, although all the ingredients are up here. So I just wanted to take a moment and show you what the geometry of how the recursion relations look in momentum twister space. So in momentum twisters, you have this 4 by n matrix of twisters. They're just generic points in C4, or really P3, which means you can kind of visualize them, maybe. So that means that suppose we have a bunch of twisters. They're inside P3, so they're 3-dimensional. We can kind of move them around. They're ordered. The ordering is very important. So there's actually kind of a circle of points in twistor space. And it doesn't matter where they are. There can be a complete generic configuration. And by this map, they define on-shell momentum-conserving lambdas and lambda tildes and mu eta tildes. OK. So, and they have some labels. So let's say we have particle 1, and then dot, 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 a minus 1 to a, and that. Now, the BCFW shift in momentum twisters is a little bit easier because you don't need to, because momentum conservation is always the case. So the shift for BCFW is that you shift Zn to Zn plus alpha times Zn minus 1. That corresponds to the bridge that we had on the previous lecture. That's what the translation of it is. So all you do is you shift this. And what happens when you shift this is that eventually you can hit a pole. So n hat is some function of alpha. And as you slide along this line, you eventually hit poles. And poles correspond to these factorization channels when consecutive sets of momenta go to 0, which geometrically, if the determinant of 4 vectors is 0, it means that they're collinear, or they're coplanar. It means they span a lower dimensional space. So what happens is that when you do this BCFW shift, you get the points where you have factorizations are solutions to the following n hat of alpha 1 equals 0. So all of these physical poles. And you can see this geometrically. So as you slide n down, eventually it'll hit some point down here where something interesting happens. In particular, it hits this plane which is the plane 1, A minus 1. Okay? And when it hits that plane, something interesting happens. In particular, there's also this plane 1, N minus 1. Okay? And these two planes intersect along the line 1, N hat. And because the line A minus 1 intersects the line 1, N hat, you can define a new point. So these two lines intersect, and you can define a new point, A hat. Now, A hat, this is where these definitions come from. A hat is the place along the line, so it's spanned by ZA minus 1, but it's at the particular place along that line where it intersects the plane N minus 1, N, and 1. Okay, so that's how you define A hat. Okay, and N hat is similarly defined as the place along the line N minus 1, N, where that intersects the plane 1, A minus 1, A. Okay, so that's your new configuration. And because you have a cycle, a full circle of twistors from 1 up to A minus 1, A hat, that defines one momentum-conserving set of momentum-conserving set of lambdas and lambda tildes. And on the other side, A hat all the way up to N hat is another one, which is why there's this interesting asymmetry here. So you see, the left amplitude involves one shifted variable, and the right amplitude involves two, from A hat up to N hat. Okay. So with that, I think we're about to get started. And the idea here, as promised, what I'm about to do for the remainder of this lecture is to sit down and open a fresh notebook. I'm going to quit Mathematica, so nothing is running. I will even do it the old-fashioned way just to prove to you that I'm quitting it. Okay, I don't want to save anything. Okay, so we have a completely fresh Mathematica. We're going to open up a blank notebook. It's blank except for that I formatted it nicely for us. And we're going to do it in basically 3 steps. The first step, which is going to take us about half the time, is we're just going to encode formula star, the recursion relations, symbolically. So basically, you don't need to know anything about these twistors that we've talked about at all. All you do is you just put in this formula, follow your nose, and you just want to, get a representation in terms of these R invariants for the amplitude. And then in the next part, I think we'll take a break after that. In the second part, we will convert the R invariants into standard superfunctions according to the definition up there. So each R invariant has a one fermionic delta function, which means it's one row of this matrix of delta functions. And then the bosonic part is very simple. It's just the product of all the cyclic things. And then I think this is actually the most important part, and it's the easiest one to overlook. But in the last part, we are going to internally check that we didn't screw up. And not making reference to any other packages or anybody else's code. Often in this business, you're computing something that nobody's ever computed before, and you want to make sure internally that you didn't screw anything up. Before you write a paper about some new amplitude that you calculated, some new process that you calculated, you want to internally check. So that's what we're going to do at the last step. We're going to verify that what we did makes sense internally, and we're going to do that by checking that different representations agree, which is a pretty non-trivial check, and then we'll also check that spurious poles cancel, which is a pretty non-trivial check. And if I don't screw up, we will pass those tests. Okay, so without further ado, I'm going to get started here. In the memo, there were also some formulas or some particular functions in Mathematica that you might find useful. If you're unfamiliar with them, don't worry about it. If you were taking notes, I would just encourage you to take notes on the things that look new or that you might want to dig into later. These are some of the functions I'm going to use, and I suspect this notation is going to be the most annoying to most of you. But all the functions, if you haven't seen it before, you can just hit a question mark and find out by hitting question something. You'll get the help file and explanations. This notebook will be sent out to everybody as soon as we're done. So you can have and I'll try to document it as we go. Okay? Let's get started. It's always kind of scary to get a fresh notebook. All right. So we're going to basically try to do it completely symbolically first, this first step. So symbolic tree level recursion in momentum twisters. And our goal is to define a function, call it R amp, a function of n and k, which returns the n particle n to the k MHV amplitude in momentum twisters. In particular, the momentum twisters Z1 up to Zn, so the standard one. We're going to encounter some non-standard ones in a few moments. Given as a list, I'm bold-facing functions that are functions in Mathematica or that are useful. So, so given as a list of products of R invariants. R invariants for ratios or something, but anyway, it's this R thing, this 5-bracket kind of object. And very importantly, check that we're right. That's going to be our kind of long-term goal here. So let's get started. The basic idea here is recursion via, we're going to implement this via iterated replacement. This is not the most efficient method, but it is a very easy one to explain and understand. So notice that inside the recursion relations, the amplitudes appearing on the left and right don't have twisters 1 through n. They have some other subsets. So in recursion, we encounter amplitudes whose arguments are mislabeled, are variously labeled, and involving shifted twisters. So we need to have something, so we need to carry this information. So strategy. Consider starting from some completely symbolic, and it's going to be important to me that it's always forever symbolic, that you never actually tell Mathematica what this thing is, object amp, which is different from this R amp that we want to build, which is k, and then has some dependence on leg labels. Then just iteratively, repeatedly replace this symbol with the right-hand side of the recursion relations. Okay, so this is our first start. We're going to build a function called BCFW recurse. And what it does something very simple. It just takes an amp with some k and some leg labels. N to the k, yep. And then it's going to replace it, but it's going to replace it delayed. I'm sure you all know this function, that arrow. And if you put a question mark, oh, it doesn't actually know what it is. But I know that if you do this, it tells you that it represents a rule transformation, but it only evaluates, it's like the difference between colon equals and equals. If you're unfamiliar with Mathematica, it's a delayed rule. It implies the right when it sees the left. So let's give it some options. So the first case that we might consider is that MHV amplitudes are 1 in momentum twisters. So if k equals 0, we're going to turn 1. And then we have that worse than MHV bar amplitudes are 0. So the way which works is the first thing is a test, and then it returns something. So in the next case, we could say if k is greater than n minus 4, then return 0. And some of you might already notice that I did something silly there. I don't have an n defined. So n is just the length of the leg labels. I could define an n somewhere, but it doesn't really matter. And then else is always a little weird in this which setting, because it always needs an even number of tests. It tests something, then it gives something. So the last case, the test that has to have is just going to always pass. So I'm going to say if true, which is always true, then use the recursion relations. So the recursion relations, we have amp, the same k, but not over all the leg labels, just the first n-1 of them. And some of you might know how, if you're familiar with Mathematica syntax, we can say like range 7. The last entry of a list is labeled by the -1th entry, so 7. The -2th entry is 6. And if you want to chop off the last thing, you can take the first entry up to the -2nd entry. So leg labels 1 up to -2 will give us that first line of the recursion relations. The same k, keeping the k fixed, lower n. By the way, this in momentum space corresponds to the 3-1 amplitude on the right. So it's one of the terms in the recursion. And here it's a pole at infinity. OK. So then we want to sum. And I want to do this very abstractly just because we're going to build this in stages. So BCFW bridge is going to build us the thing inside the summand. So it has some indices, so term indices, and it depends on the leg labels. And the term indices will range over something that I'm going to actually partition off just to save myself some sanity. And I basically just want to encode all of the terms that appear on the right-hand side. And I'll call that BCFW partitions from n and k. But again, we don't have an n defined, so we'll call that length leg labels. OK? Good. So we just need to define. So it starts at the beginning, and it's the first one that passes true. Yeah. Yeah. Good question. Sometimes I forget to put this last true before the last thing, because I think of it as if then else, but which doesn't behave like that. It always needs to find some task that passes. OK. So now what we need to do is must define these ingredients. BCFW bridge and BCFW partitions. Let's start with the latter, because it's going to be a little bit easier. So partitions across the bridge. So the idea here, so our goal here, is to generate a list of all the, or enumerate all of the terms that appear in the summand of recursion. And we can encode these any way we'd like, and I'm going to encode them slightly redundantly, but in a way that's just going to be useful later. I'm just going to simplify our life later. So I'm just going to say the n left, k left for the left amplitude, and then n right, k right. Right, these things are related to each other, so recall or note that n left plus n right is equal to n plus 2, and that k left plus k right is k minus 1. So these things are not independent of each other. But we're just going to kind of generate a list of these things, which are just the indices that appear inside this bridge. So when I program, I like to, if I'm going to have a variable, I sometimes like to pick a particular case to build. And for moral reasons, you'll never find me coding n equals something inside of a global variable. But I sometimes like to build with an example. So let's consider the n equals 8 and k equals 2. And we want to generate a table like this. And it'll be n left, n right, or k right, k left, sorry. N right, k right. So we just want to generate this kind of list. And we can do that from n right goes from 4 to n minus 1, and k right, so that'll generate that kind of table. And then k right runs from 0 to n right minus 4. Now there's already something a little bit, I need to process this a little bit, and you can tell if you look at the first entry of this table, you find something close to what we want. But if you look at the last one, you can see what's going wrong. The output of table actually gives you nested lists, and so if you have nested sums, it gives you nested things. And so I want to flatten this, and there is a function called flatten1, although I might as well use it. And that will now give you a list of terms. It'll take this iterated list and give you a single list out. OK, good. But again, we know what n left is in terms of n and k. So n left is n plus 2 minus nr, and k left is k minus 1 minus kr. Okay, so now we have a list of terms. But you can tell that this is a 3-particle n to the minus 2 MHV amplitude. That's not something we really care about. So let's select from this list only those terms that are non-vanishing Q, which is like question. So imagine we want to apply. So the way select works, if you haven't seen select, is that it applies a test, a functional test, to every object in a list. And if it passes, if it returns true, it says keep it. And if it returns false, it throws it away. Or if it returns not true, it throws it away, which is slightly different. So we can apply non-vanishing Q. We want to, this is where some of this notation that might scare you is going to, I hope you'll become more comfortable as the end of the hour goes. But if I just, did this, it would multiply, it would take this symbol and multiply it by this line. If I put an @ sign, it applies a function to it. And so you see that it just, non-vanishing Q is now a function that eats what the previous line was. If I do it twice, it does something a little bit more interesting. It strips off the outer range, and now it's a function with 2 slots. That's not what I want either. I mean, I could define that function, but actually I want 3 ats. And if you're not very familiar with that, that does that. It says non-vanishing Q on the first thing, non-vanishing on the second one. Because of course, a term in BCFW is non-vanishing if the left and the right have to both be non-vanishing. So we really want this to be our test. If this is a non-vanishing amplitude and that's non-vanishing amplitude. Now, this is where another thing that you might be unfamiliar with comes up, which is that I want to define this as a function, but I don't want to give it a name. I just want to use it inside select. And the way to do that is to think about, how do you partition this? This is a function that eats that thing. How do you tell Mathematica that that's a function? One way to do it is to try parentheses, and it will immediately show you what you're doing wrong. So if you put parentheses around it, this is not a function. It's not in the right syntax yet. However, it would be if you need to give it an argument. You could say, like, for example, function of x, and then put an x here, and then that works. Or you can use that is good notation, so I will use that notation. So we want to apply this. We haven't defined it yet, what non-vanishing is. Okay, so non-vanishing Q for the n particle k, n to the KMHV. The first part is pretty easy, which is that k has to be greater than 0 and it has to be less than or equal to n minus 4, which is the criteria that we had before. Worse than MHV is 0, worse than MHV bar is 0. But this is a source of a potential bug that you would have to catch later, but I've done this enough that I know where the bug is going to be. So there's an exceptional case here that would fail this test that you definitely want to keep, which is when n and k are 3 and 0. The 3-particle MHV is definitely allowed. You want to keep that. So keep that there. And now we see that, let's see, what did it do? Cannot assign a raw object to, I put an equals sign, which is not a test, that's a setting. Okay, so it says this is not a non-vanishing amplitude. So we select from our big list all of the things that pass this test, and we get a sorter list, and indeed, everything passes. We can even put that over all of them and see that everything gets true. Okay, so BCFW partitions, we're done with this. N and K is this function. And that's why I use the with, so that now I don't have any unusual variables or fixed parameters there. I can just copy it in, and it's a general function. Good, BCFW partitions. And I want to take a short aside. It's actually secretly a way for me to make sure I didn't make a mistake, but it's also kind of fun, and it's useful for some of the homework at the end to improve this. Counting terms in BCFW. In the last lecture, I gave you a closed formula for this. So there is one. It's in terms of the Catalan numbers. But the idea, we can do this very simply recursively. So again, we're going to take with, n equals 8, k equals 2. I know that there are 20 terms in BCFW, but we're going to count this by brute force to see if we're right. So we have this BCFW partitions, n and k. And we'd like to apply the number of terms. So the number of terms in BCFW that we're going to get is the number of terms in this amplitude times the number of terms in that amplitude, plus et cetera. And this is one of these cases where you might just figure out how the ats work by just keep adding them until something works. So terms in BCFW, if you do that, it just applies it to the whole list. If you do that, it kind of applies it the right way. All right. If this is unfamiliar notation, this is very useful stuff. Anyway, so now I've got terms in BCFW on each piece, and I want to multiply them together, so I'm going to put times. And now it's a list of products of this undefined thing, terms in BCFW. So we want to total that thing, and that's part of it. But it's not the whole answer yet. Why? Because it's also, we need to have the terms in BCFW n-1k, the same n-1 and k. And this should recursively work. So let's try. Terms in BCFW, n and k. Again, a which. If k equals 0, there's a single term. We can just truncate this recursion there. If k is greater than n-4, there are no terms in BCFW. And if everything else is just true, we put in this formula that we just figured out. All right, so let's see if we did something right. The 8 particle n squared MHV amplitude, 20 terms. Perfect. That is actually the right answer. And if you copied it from the previous lecture, you could test that. Let's look at the 14 particle k equals 5, n to the 5th MHV amplitude. 19,404, that's also the right answer. So good. But you'll notice that this is a little, you might have noticed a pause, and it's actually kind of interestingly annoying. So if you wrap something in timing in Mathematica, it gives you the output, and it also tells you how long it took. And it says 0.57 seconds. Oh my gosh, that's actually pretty gross. And the reason is because in this formula, every single time it sees terms in BCFW, it starts from the very beginning and doesn't store anything. So aside, speed things up. The idea is store intermediate results permanently, well, not permanently, in memory. And we can do this, by using a function you probably all know, which is set, which is the syntax equals, by calling set after set delayed, which is a formulation you probably are not used to, but it's more familiar, just colon equals. So set delayed. So let's clear this out so we don't have any definition of this anymore. So clear all terms in BCFW. Now the blue tells you that Mathematica doesn't know what the symbol means anymore. And we're going to copy this. And instead of just colon equals, which means when you see the symbol feed in the right-hand side, I'm going to actually wrap the whole thing in an equals, in terms in BCFW nk equals. And now what happens, you don't need the parentheses here, it's just for visuals. What it does is the first time it sees it, it doesn't know what it is, it applies the right-hand side. Now what does the right-hand side do? The first thing the right-hand side does is it stores it in memory, that equal sign. Stays it forever, and then it does the recursion. This is a way to speed up a lot of things that we're doing later that I'm not going to have time to speed up. So we can already see that we improved something by checking this 14 k equals 5 amplitude. Instead of 0.6 seconds, we get 0.006 seconds, a factor of 100 improvement in speed. And just to prove to you that it really is stored in memory, if we do it again, it says 10 to the minus 6 seconds, which is a little sad. I mean, it's disappointing my computer takes a whole, 10 microseconds to look up a number like that. But anyway, 7 microseconds, worse. Okay, so this will work. And this kind of idea will help you later if you'd like to improve this notebook when you go home later. Okay, so now we need to get back to the recursion relations. And we're missing this BCFW bridge, which takes the indices and returns this product, this whole big product structure. And the basic idea is we want to explain what's going on inside this summoned. So we'll just kind of copy that in just for visual reference. And again, we can try with n particle. I love the 8 particle n squared MHV. It's probably my favorite amplitude. I've certainly spent a lot of time with it. But instead of summing, I want to take, well, actually, I'll just take the exact same thing. Yeah, okay, let's do this. Instead of n equals 8, I can say leg labels is range 8, because this thing doesn't have an n in it, right? So I'm going to do this, but instead of summing it, I'm going to do table. And what you see is this is what we want to get. We want to get this list of terms. So we need to define a function BCFW bridge that has this kind of data structure. It tells you what the leg labels are, and it tells you what the n left, k left are. So let's, I should probably comment that out, because we don't care about it very much. So BCFW bridge. It depends on n left, it depends on k left, it depends on n right and k right, and it depends on leg labels. And now I'm going to use one of my favorite environments. If you prefer modules, I will fight you, but there's a debate there's a whole beautiful block versus module debate in the documentation. You should all read it. I'm actually not very opinionated, but I like the colors of block a little better. Anyway, just not a, anyway. So what block does is it gives you a temporary environment with temporary variables that you define right up here at the front. And so like one useful symbol that we might use in this formula is like n, which is the length of the leg labels. Okay? Another thing that's kind of useful is like the left labels and the right labels. And we're also going to need this a hat thing and an n hat thing. Okay. So the output of BCFW bridge, I'm going to have a product, but I don't want it to actually write it as a product right now. I want it ordered for visual reasons. So I'm going to use lowercase times, which Mathematica doesn't know what that is. I like keeping Mathematica in the dark. So we have the left amplitude with some left labels. And then we have some R invariant in the middle, depends on something, and an amp k right, right labels. Okay, so now we've defined our bridge. We go back here and we say, it's the product of this, that. Okay, it doesn't look much, still kind of boring. So let's define our label ranges. So left labels are just the first n left labels from the big one. So leg labels, 1 up to n left. At first, we're going to add the hats in a moment here. And then the right labels are similar. They're the leg labels from minus n right, so from the end point to the last thing. And now we can see, okay, that's starting to look a little bit more normal, that output there. Now, the arguments of the R are just a few of the leg labels. And in particular, the first one, a minus 1. Oh, I didn't define a. I'll do that in a second. Yeah, another useful symbol in this thing would be a, which is just n left. Okay, so now we've got this. This is looking kind of okay. So these are the R's in the middle. And now we need to do these hats. And the first thing to do would just be to replace an entry of a list. There's a function called replace part, which literally just surgically takes an expression and inserts something somewhere. And if we want to take the last entry, it's the -1th entry, we can say replace it with a hat. And for the right range, we want to replace part, we want to do two replacements, which is we want to take the first entry and call it a hat, and we want to take the last entry and call it n hat. If we do that, we see, okay, that's kind of looking okay. So this is our terms now, the partitions across this bridge. And all we need to do now is to define what these hatted things are. And actually, I'm going to be mostly symbolic for this, at this stage. We're going to be much more explicit at the very end. But right now, we want to stay symbolic. And so the idea here is for the hatted things, just insert the definition symbolically as it's been given to you. Just use the formula symbolically. So we have some a hat, which we're going to define as, it's symbolically given as a minus 1 a intersection with n minus 1 n 1. And here's where I'm going to define a new symbol for this thing. And I'm going to call it cap for reasons I'll explain in a moment. Some of you might already understand why I'm calling it cap. Okay, so I'm going to denote this in Mathematica by this, which is still undefined. I'm just giving it a name. And similarly for n hat. So recall that the LaTeX syntax for intersection is cap. That's why I'm doing that. So I'm just going to say cap this kind of thing. And it's just, again, it's undefined because cap is not defined anywhere. I'm just going to use it as a symbol and we'll see what happens. So we can say a hat is cap, left leg labels a minus 1a, and then leg labels n minus 1 and 1. And the definition of n hat is literally identical, just with a and n swapped. So we're just going to delete those a's, put in n's, and put in a's here. Okay, now this is not going to be human readable anymore, unfortunately. Oh, something interesting happened. What happened there? Oh, left labels. Leg labels is what I needed. Oh, see, this is why you always run this kind of stuff. And I can now replace times with actual times. And this, not very useful for anybody. But we'll see in a little while if any of this stuff makes any sense. So I think we're done, if I didn't screw anything up. So let's keep going. So putting everything together, and then we'll take a break after this. So again, we're just going to apply this recursion iteratively until we're done. So let's start again with another favorite amplitude. This is not actually my favorite, but it's simpler. The k equals 1 amplitude, the NMHV amplitude. So we're starting point, this strategy from the very beginning, if you recall, is that we have an amp k, and it has some legs. In particular, the original one is just range 1 through n. And then we're just going to apply this BCFW recurse operation. So we are going to replace it with the output of this recursion, okay? And you can see that's kind of a mess, so we need to apply it again, and then we need to apply it again, and we need to apply it again, we need to apply it again. And some of you probably know that there's a shorter way to do this in Mathematica, which is to put // dot. That does it until it stops changing. So we've now got a list. It looks even right, but some of you might not recognize that as right. But anyway, so we've got a list of terms. Great. But remember that we wanted a list of terms, aka monomials. So we'd like to just, instead of getting a sum of things, we just like a list of things. And we can do that by, sometimes in Mathematica, especially now that autocomplete exists, you can just start typing and see, you'll discover that a function exists. So, monomial, oh, there's a function called monomial list. Good. I bet that does what we want. And it does. Okay, so monomial list. And now actually we're pretty much done. So with this part of the n and k, which is just that. We would be done, although I really want to be able to verify that we didn't make a mistake. And to do that, I want to exploit a property that really, really must be true. Things up for fun. Which is that if we did things correctly, then amplitudes should be cyclically invariant. Even though these are very non-manifestly cyclically invariant. So let's test this by randomly rotating the arguments of every amplitude every time we see it, of every amplitude. This will give us randomly generated recursion relations. So let's see how we would do this. So now it's all about the leg labels. So leg labels, let's say that it's like range 7. This is just to show you how this would work. So I want to randomly rotate it, and rotating is a function that's not the right one. If you look at rotate, it rotates a 2D graphics, not very interesting. But if you do autocomplete, there's a rotate left and a rotate right. I don't know what rotate label is, but I'm sure that's the wrong answer. So let's do rotate left, which we can check actually what it. So if you find a function, you don't know what it is, you put question mark in, and it'll tell you what it does. So rotate left, if we apply that there, it just rotates the indices by 1. We can also rotate it by 2 or something else, but now you can kind of see I want to randomly rotate it. So I want a random integer, and I want it to be 1 through n, but I happen to know too much about Mathematica to tell you that random integer goes from 0 to n, so you need to minus 1 if I want a flat distribution. Okay, so now this is a randomly rotated thing. I'm taking the leg labels and I'm just mixing it up by a random amount. Perfect. So we're actually ready to go. BCFW recurse random instead of the original one. Now we're going to take this amp k leg labels like we had before. But before we actually do anything to it, we're going to take k and we're going to randomly rotate these labels. We're going to take that. And then we're just going to apply the recursion that we had before. So BCFW, this is OK. FW recurse. OK, and we can now have a R amp. So an amplitude represented in terms of R invariance. We can do this randomly. So I'll have an R amp random, which does the same thing but recurse random. And let's see if it even looks like it's behaving correctly. So like 8 particle NMHV amplitude, you get 10 terms there or 10 terms there. Ah. OK, so now you can start seeing where we're going to find how to test this intrinsically. Because we're going to be able, once we get, after the break, we're going to convert these things into functions that we can get components out of. And if these, now we're going to get some really magical identities among rational functions that we're going to test. And if all of these things give you the same amplitudes, it's probably a good sign that you didn't screw up. So at that point, it's about halfway. It's more than halfway through the lecture. But let's take a 5-minute break, and we'll come back and start at part 2.